Good evening, all of you. My name is Anil Yadav, and today it's 10th tutorial of Fundamentals of Micro and Nano Fabrication. And I am following the lectures of Professor Shankar Kumar Selvaraj and Professor Shushuban Awasthi, and also I took the notes from their lectures only. So let's get started. Today we will see the basics of lithography, mainly the optical lithography, that is the simple pattern transfer optical lithography, that can be contact lithography, or there is a gap lithography. We won't go towards the far field lithography. For that we have discussed in the previous lecture as well. So today we will just discuss about that near field lithography, which is kind of in contact lithography, and then we will briefly see the whatever we have seen in the last lecture, that was the etching, that subtractive part of the etching. Okay, and before that there comes a metallization, and there comes some things, so that we will briefly tell I will briefly tell about all those things as well. Okay, let's get started. So first actually, what is the lithography? Lithography is the transferring of the pattern. Okay, whatever you have, let us say just you want to make a same pattern on a lot of substrates, just say substrates, or like you want to print the t-shirts. Every time you are not making kind of the t-shirts, right? So what you can do is, that is transferring of the pattern. Okay, like that is a transferring of the pattern. That is also a lithography. You will make a mold, or you will make a stencil kind of thing, that, and through that you will just print that. That can happen within a second, within seconds you can transfer the pattern. And that same logic we are applying for the devices, how we make the devices. Okay, so in lithography, that like on this cylinder, okay, on this cylinder there is a pattern over that, and if we put some ink over that, there are grooves on the cylinder, that is the pattern, and we roll over something like paper or clothes somewhere. So that pattern, whatever on the cylinder, will transferred on the paper or whatever that there is underneath. Okay, and the same thing, this is kind of a roll to roll printing that happens in like newspapers. Okay, newspapers like this, newspapers are like printed. Lithography is printing only. Okay, so check on is there. So as you can see in this picture, so the same picture she is drawing over the wall. So she just made a kind of stencil, so there are openings on the over the paper, and she is just rubbing that paper, rubbing that kind of stencil with ink. So wherever there is opening, so that pattern will get transferred over that. Okay, and there the same thing is with that you have seen kind of a stencil that you might be having in your nursery classes, or just kind of writing your names with these stencils. Okay, so initially we will go through the pattern transfer needs photoresist processing. Okay, the very first part for the indirect kind of lithography, we will touch about the first. We will see the photoresist processing. Now we will see what is the photoresist and what type of lithographies are there where we need the photoresist. Okay, so pattern transfer, so we are through lithography we are transferring the pattern transfer. There are several methods. One is direct method, one is indirect method. So in this direct method, what happens is we just write directly through the laser, through the electron beam, or any kind of thing. So we can directly write over that, like with the pencil. Okay, with the pencil you are writing directly over the paper. Okay, that is the direct writing. Okay, if there is something in between your paper and there is sacrificial kind of layer is over there, so to transfer the pattern, okay, that is the indirect method that is required for the devices. Okay, for over a large area we can do, and this kind of lithography. Okay, so what we have is we, in our mobiles that we get smaller and smaller devices are there, so they just get printed. Indirect printing method, that is the optical lithography. Okay, there are two things comes, which is contact lithography and projection lithography. So today what we will see is the contact lithography. Okay, and we will see there is a photoresist that is used for the contact lithography as well as for the optical lithography. There is a need of the of the of this photoresist. Okay, so we will see that. So so what is the idea of patterning coming out? So there are two types of patterning. One is direct patterning, one is indirect patterning that we have seen. So ion beam milling. So directly, if you have something silicon and silicon dioxide, and from the particular parts of that wafer you want to remove the silicon dioxide, okay, there are two ways of removing that. Just directly remove the with the ions, beam of ions, just directly remove that area. Okay, that just make the grooves directly. Okay, just think of you have a scriber. Okay, and you are just scribing the wafer over that, and you are just making the grooves. Okay, the ion beam milling does the same thing. Laser writing of the polymers. Okay, directly writing the with the lasers, and sometimes the ITO etching. Just removing the ITO from over the substrate that you can do, and scanning probe lithography. That is kind of AFM, from the AFM tip that can be used just to remove the material. That is also a scanning probe. And in indirect patterning, what comes is there is your substrate, and in between, and we coat one more layer over that. Okay, over that. So that and okay, so there is SiO2. This is SiO2, and this is photoresist. Okay, this is known as the photoresist, and photoresist is has a property of changing the properties of the resist with when we shine the light. Okay, when we shine the light of the particular wavelength with certain amount of energy, okay, that will change the properties of this photoresist. Either it will get hardened or it will get softer. Okay, that depends on the what kind of photoresist you are using. So accordingly you can remove the material from the certain portions. Okay, that is the this sacrificial layer. From the certain portions you can remove, and further you can remove this material from this from SiO2. So what we have used is the photoresist. So the use of photoresist is such that it will protect the other areas for further processing. So that is the indirect patterning. First we will make the pattern over the photoresist, and then we will do the next step. So that is the indirect patterning. So indirect, but this is the indirect patterning process flow. First there is a substrate that then when we will this substrate we will coat the photoresist. This is nothing but photoresist. Okay, and then we will bake this substrate. In the sense we will, after photoresist, this photoresist is like there is a sensitizer. Okay, that sensitizer is there, that is kind of a material, and that sensitizer is dissolved in some solvent, and that after that we spin coat it, or we just coat over the substrate, and then we anneal it. Okay, someone is there, I guess. No. Okay, so we bake the substrate. Okay, so just to remove the solvent, or to make the to remove the solvent. Okay, and then what we do is this is the photo mask that we can prepare. So so there are openings in the photo mask. This is the photo mask. So through wherever there is opening, so through that light can be pass. Okay, through that light can pass. So then we shine the UV light through this. That UV light will through this. So through this part, the UV light will go inside, go and change the properties of the photoresist at this point. Okay, and this part will get as it is because there is no pass of the UV light through this one. That is opaque to the UV light, and this will change the properties here, and then we will remove from the photoresist from a particular this point, and then we will do the subtractive process that we will see later. This subtractive process will remove the material particularly from there, from this point, because the process that we are using here, either dry etching or wet etching, that we will see the wet etching today. So that will remove this photoresist. Photoresist will protect the layer underneath this one, underneath the photoresist, and this is exposed to the outer environment, right? This is exposed at this point to the outer environment, then that will get removed from here. Okay, that is the this is substrate. So finally we will remove the photoresist and we will get this kind of pattern that is transferred to. So the indirectly we did this thing. We are not directly from this step to this step, we are not reaching. Okay, so indirectly we are first transferring our pattern to the photoresist, and then we are transferring our pattern to the substrate. So let's say see the optical lithography. How does this process happens? Okay, so in optical lithography, there are several optical lithography systems. So these are kind of lithography where you do not, these are near field. Okay, near field diffraction photolithography kind of. So in this one, what happens is the mask that we saw in the previous slide, that was a chrome mask. Okay, in chrome mask what happens is there is a glass. Okay, there is a glass that is the size of the mask, whatever 2 inch, 3 inch, 4 inch, 5 inch, whatever the size of mask you want to use, and over that there is a coating of chrome coated. Okay, and we have already patterned with this mask. Okay, we have already patterned this mask. This is chrome and this is the opening through the chrome. And what happens is chrome is opaque for UV light. Okay, UV light doesn't pass through the chrome, so so the UV light will pass through the openings here, and that is placed over the wafer. This is our wafer, that black color. So UV light will pass through the wafer to the wafer through the mask. Okay, so whatever the pattern over the mask, that will get transferred over the wafer. Okay, and this wafer is nothing but it is coated with photoresist that we have seen. So first the pattern will get transferred to the photoresist, and then we can do whatever we want to do. We can do the additive process, we can do the subtractive process. That is that depends on what kind of devices we are making. Okay, so another one is the gap lithography. There is a small gap, very small gap in just few microns, like 4 or 5 microns kind of. So that there is a small gap in between this mask and this wafer. This gap is we deliberately keep this gap, and that is because of this mask should not get scratched by the wafer. There may be some particle. Okay, so all this process is done inside a clean room. Okay, so where there is very few particles or no particles, so that in this kind of dusty room there are lakhs of particles around in 1 metric cube of the volume. Okay, but there are classes of the clean rooms that we discussed in the very first class. So so this kind of clean room is used so that there should not be any particle. Okay, otherwise that will kill the process. So in this one what will happen is now there is a gap, so it will not contaminate our mask. Okay, otherwise it will get scratched, and that scratched pattern will also get transferred. Okay, that it may scratch the chrome out of this mask. So this is the so also we can say the lifetime of the mask. Okay, how many times we can transfer the pattern without getting our process screwed. Yeah. So and another one is this projection lithography. In projection lithography, that we have 2 classes back we have studied this projection lithography. In projection lithography, what is there is, so for around 4 to 5 times of less features size you can get over the wafer, whatever there is on the mask. Okay, let us say you have 2 micrometer of feature size in the mask, so then that you can transfer 500 nanometer of feature size to this substrate. That is the beauty of this projection lithography. With the projection optics, that is kind of very typical. So the highest cost of fabricating devices is the lithography process. Okay, so and also beyond that there is one more thing, which is more lithography plus this UV light. Okay, this UV light is very expensive. Here whatever we use, that is very expensive. Okay, we will see. So now what is a photoresist? So as I showed you, that material that absorbs exposed light. Okay, this is the absorption of the light in this region only, in this particular region, the absorption of light, and that changes the properties of the photoresist. This light changes the properties of the photoresist, so it will get dissolved. Okay, that is the positive photoresist, positive PR, that will get dissolved in this in the developer solution. The solubility of the photoresist changes with the exposed light, so we have transferred the photoresist pattern on the photoresist. Okay, now we can do anything. If we want to deposit gold at this particular point, we can deposit the gold and then we will remove this. So whatever there will be gold over this, that will get removed, but this area will be saved for the deposition of the gold. Okay, and there are so many steps in the lithography. So let us see what are the kind of steps in the process of lithography. So first, wafer cleaning. Wafer cleaning is a bit typical. So what I can say is, in wafer cleaning, wafer is cleaned like there are some steps. If you want to do the RCA cleaning, that we have seen, RCA cleaning, RCA 1, okay, RCA 1 and RCA 2. This kind of this is the cleaning process, RCA 1 and RCA 2. This process is mainly done for the diffusion, or we can say dry oxidation, because this process is when we take the new wafer, then we do the RCA cleaning and then we do the diffusion on oxidation. And for lithography, mainly we do the solvent cleaning. In solvent cleaning, what happens is, in the solvent cleaning, what we do is we dip the wafer in we actually ultrasonicate the wafer in acetone. First in acetone 5 to 10 minutes, then IPA, then DI. We rinse with DI water. So that will remove the whatever particles are over there on substrate. Okay, so that will help to reduce the contamination because of the particles. Okay, then we do the dehydration bake. Dehydration bake is there is adsorbed water over that, so then we need to remove that adsorbed water. So about above 100 degrees Celsius for 5-10 minutes you can do the dehydration bake, and then we need to give time for the cool down. Okay, then we do the coating of either HMDS or surpass to for the adhesion. This is known as the adhesion promoter. So after the dehydration bake, when if we directly coat the resist, that resist may not uh, be coated properly over the substrate. That is because of there may or may not be good adhesion of the resist with the substrate. So we put the adhesion promoter. Okay, then after resist coating, that we do the spin coating. If your wafer is kind of a square type or whatever, so at the edges of the wafer, there are some beads. This is kind of the edge beads. The thickness of the wafer, no, see, thickness of the photoresist material is more at this side, so we can remove these beads by uh, uh, finally we can increase the speed of the our spin coating speed just 5 seconds, and then we at that point these AS beads get removed, or we can just with the buds also we can remove this, but that will affect the this layer. Okay, so there are some methods to do that. Then pre-exposure bake. After the coating of the photoresist over the substrate, then we need to remove the solvent, so that is the soft bake. Okay, pre-exposure or soft bake that we can say, and that is done around 110 degrees Celsius. For that also, that this temperature depends on photoresist to photoresist. Okay, at 110 degrees Celsius you can do the baking at for 1 minute. Okay, then again you need to give some time, cool down time, and then you need to expose through the mask. Then again cool down, because of the exposure there is a absorption of light, and that absorption will increase a small amount of the temperature. Then we do the post exposure bake. Then again cool down, then we will develop it in certain solution, and that will remove the certain part that is either exposed or unexposed. That depends on the property of the photoresist. Okay, then finally we will rinse that with the DI to remove the developer solution, otherwise it will get it will do the over etching. Then we will do the dehydration bake after rinsing it with DI, and then cool down, and wafer is out, and we can do the next process. Okay, this is the process that will give you this pattern. Okay, from here, from a single wafer to this point, there are these many of the steps. These many of steps you need to follow. Okay, now photoresist. Let's see the properties of the photoresist. Okay, so in photoresist there is a base material or a resin that is there, and there is sensitizer, and there is solvent. Okay, when this sensitizer is used that absorbs the light. Okay, and which changes the properties of the photoresist, that of the base material or whatever. Okay, so now the absorption of light. So there through the Beer-Lambert's law, you can see the absorption of light that depends on the thickness of the photoresist. Okay, that depends on the photoresist, how much light is getting absorbed. Okay, so let us say this is the material thickness, and here a light is coming. So at this point, let us say the intensity of light is I0, and at this point intensity is I. So the I is equal to I is given by and this is the thickness of the material, let us say G. Okay, this I at G, at any point G, let us say G, what thickness, is equal to I naught e raised to power minus alpha g. Okay, so the intensity exponentially drops. Okay, this intensity of light exponentially drops because of the absorption of the light. This much of the absorption is left. So this light is coming, that is the transmitted light. Okay, at this point I is coming, that is the transmitted light after g thickness. Okay, so in this one now what we will see is alpha is the absorption coefficient, that depends on the material to material. What is the absorption coefficient? How much this light it can absorb the light, how much light it can absorb. Okay, so and the complex refractive index n is given by n plus ik, and this k is k depends on this this alpha depends on k for the particular, for the various wavelengths. Okay, so let us say we have not a single material is there inside this. Okay, so not a single only material is there in the thickness of the whatever you have coated. So there is sensitizer, there is some resin material, there is some solvent. So the absorption coefficient alpha whatever we have, that total absorption coefficient will be equal to alpha c alpha 1 c1 plus alpha 2 c2 plus alpha 3 c3. Okay, this kind of sum you will get, and which is this alpha is the absorption coefficient of corresponding to that material, and c1 is the concentration of that material in that. Okay, so this is the thing. Now, so what happens to the resist when it absorbs the light? Okay, so this is the base insoluble sensitizer. So when we expose through the light, there is a reaction happens. Okay, that there is kind of reaction happens. It will remove there N2 will be released, and there will be a rearrangement, and finally you will get this kind of product. Okay, this was insoluble initially in the developer solution, but this is soluble. So wherever there will be a light in that portion, so this insoluble sensitizer will convert it into this soluble photo product. Okay, so this will this will get dissolved in the developer solution, and we will have some kind of pattern over the substrate. Okay, so that pattern is in the photoresist. So for the further processing, this insoluble base can protect the layer underneath, and whatever we have patterned that converted into this one, and that is removed already. Okay, so now let's come on the tone of the photoresist. So I was keep telling that which part will get soluble, which part won't get soluble. That depends on the tone of the photoresist. Okay, if there is a positive tone of the photoresist, the area which is exposed to the light, that will get dissolved. Okay, so that will get dissolved. So, and in another part, if the photoresist is of negative tone, so what will happen is there will be a cross-linking. Cross-linking means in the sense there are chains of the polymers in the photoresist. Okay, so there are the chains like this. Okay, so these chains will get removed if we directly put that in the solvent. Okay, not in the solvent, in the developer solution. Okay, if you are not shining any light and you directly put this wafer in the developer solution, everything will get removed. Okay, so but as soon as you shine the light, this part will get cross-linking. The cross-linking in the sense these chains are linked through each other. Okay, through with each other through some chemical bonding. These chains are so now when we put this in the developer solution, so this is got hardened, so the cross linking happened, so this got hardened, and this won't develop. Okay, so because of the cross linking, this will stay, but other part which was not exposed to the light will get removed. Okay, this is the negative tone photoresist. Now now after this okay, wait. After the UV exposure through the mask, okay, after we have done the UV exposure through the mask, we do the annealing. Okay, annealing. There are two things. One is pre-bake and one is post-bake. Pre-bake, which is also soft bake, that is done after just coating of the photoresist. Okay, this pre-baking, so we can vary the temperature of the annealing temperature, right? So that also has the effect on the photoresist. So the temperature and atmosphere. Okay, if there is a very high humidity, that depends on this humidity, sensitizer decomposition, temperature. If the temperature is too high, sensitizer may get decomposed. Okay, so that also happens, high or low, that depends. And also the atmosphere, in atmosphere there is water. Okay, that affects the this development things. Okay, when we do a higher level of the water or humidity in the environment, that will give you absurd results that we will see. Okay, solvent diffusion and evaporation. When we do the temperature, we increase the temperature, solvent may get diffused through the sides or something may happen. Okay, that also the post exposure development, that will have effect on the post exposure development. Okay, so all these things will affect the post exposure development. When we do the development, we remove the photoresist. At that time, the feature size you were expecting may or may not come properly. Okay, so now let us see the resist contrast curve. Okay, what I was telling you is one thing, that a certain amount of energy of the light is required to remove the photoresist. Okay, so initially this thing, this is the energy. Okay, this is the removal of the film. Okay, let us say this is the thickness of the film. Okay, that is T. Okay, so initially the film is not removed completely, the thickness of the film remaining. Okay, that is T. Let us say this point is T, thickness. Okay, so this is the energy, even energy of the light that you are giving. That is the like 70 millijoules of per centimeter square, 60, 50. So whatever the energy is required, that is the millijoule per centimeter square, the energy is given. Okay, so initially the energy is very less. Okay, energy is very less, that is not able to remove the photoresist at all. So then what happens is we increase the energy, so it started removing the photoresist. So then there comes a point when above that energy, this E naught, whatever energy let us say this is 70 millijoules, 70 millijoule per centimeter square. Above this energy, whatever 80, 90, whatever dose you will give, that will remove the photoresist completely, like this. Okay, this is the removal of the photoresist. The blue part is the removal of the photoresist. Okay, in this one it has not removed completely, in this one also, in this one also. So we are increasing the energy in this direction, and this is the thickness, decreasing of the thickness. Okay, so at beyond this part, whatever you do, energy or dose you keep, that will remove the photoresist. Okay, so this is the contrast curve. And now development time. So development time also affects a lot. That is the like kind of a critical thing, critical parameter, the development time, how much time you need to develop. So okay, so that is critical because that maybe there may be remaining of the photoresist. If it is underdeveloped, there may be overetched, that can shrink your feature size. If there is the, but if you have increased the development time, okay, if it was required 20 seconds, you have given 30 seconds, then there will be a shrink of the of your feature size. That is the thing. Okay, so this is the simulated data which shows you, okay, which shows you the like this is the development time. Initially zero development time, there was a complete photoresist was there. Okay, then after you are increasing the development time, and you can see that there is sharpness of this feature and then there is overdeveloped. Okay, this is shrinking. Okay, that is the thing. Developer is of two classes. That is like there are metal ion containing developers like NaOH, KOH. Okay, so these are, these are available, very easily available, and these are cheaper. You can do this with these kind of developers. And another one is metal ion free developers. These are literally expensive, very expensive kind of. Okay, this is tetramethyl aluminum hydroxide kind. The TMAH stands for tetramethyl aluminum hydroxide. In this one, there is no metal, and if you are doing the device processing, kind of you are doing on the silicon wafer. So these metals, the diffusion coefficient, diffusivity of these metals that we have seen in the during the diffusion part. So the diffusion coefficient is very high for these metal ions, and that will kill your device. Okay, so that's why we should not use this metal ion uh, containing kind of developers. If for the CMOS processing, we cannot use. We can use these kind of developers if you are for MEMS purpose, for microfluidics uh, structures. You can use these kind of developers. Okay, otherwise not. Now, as we have seen, these many steps were there in the lithography. So these steps should be done in one go. Okay, from this to this you should reach. You should not give time in between the steps. Okay, if you give the time, if let us say after spin coating at this process, or you went for lunch or dinner or something, and then after coming you are doing the pre-exposure bake. Okay, which is soft bake. So the properties of your photoresist are already changed. Okay, in the meantime, so you won't get the desired feature size. So you should, whenever you are doing the lithography, you should do from this point till this point in one go. Otherwise there will be some other artifacts that will come. Okay, so the delay factor in between the processes, what can that do is, so this was the desired feature size. Okay, you wanted the feature like this, but because of the some your lunch, you would have skipped, but you didn't, or your dinner or your tea that you cannot skip. Okay, because of that you have done this kind of pattern you will transfer this kind of pattern over the mask. Okay, there is kind of T-top, there is footing. So at this point this photoresist is not removed properly. Okay, this photoresist, this will you wanted a feature size of uh, of this much. Okay, this much, but you are getting a larger feature size in this one. Okay, in this one also what will happen when you do the other processes, like deposition of gold over that, that will deposit till this point, till this point. Okay, so during that also both of these are not desirable. Okay, in this one you will get wedge kind of thing, like which so when you do the gold deposition, so this gold will get deposited over this side as well. So when you will do the lift off process, lift off is the process is done after the deposition of gold, the removal of the photoresist. Okay, this is the lift off process. So when you will try to remove this photoresist, it will be very hard to remove this. Okay, and that is because the gold is protecting this photoresist now. Okay, so this photoresist is dissolved in acetone. So what generally it is, what is generally done is after the deposition of gold over the photoresist, so this uh, substrate is immersed in gold, immersed in acetone for hours. Okay, so for some like 5 6 hours, so that will dissolve this photoresist. Okay, but the gold is protecting, and that happens when we deposit this from the top. So these side walls are not getting deposited. Okay, because of the directionality of the deposition. So but in this case these walls will also get getting deposited by the gold. So it will be very difficult for the lift off process. This is the thing. Now okay, 1 second, 1 second. Now, so resist design. So because resists are like there are so many things that can happen to the resists. Okay, so resist is kind of critical, very critical for the indirect lithography process, because we initially transfer the pattern over the resist. Okay, the sensitizer that you mix with the inhibitor. Okay, so with the resin, actually with the resin, that sensitizer, so the sensitivity of the photoresist, so how much sensitive is the photoresist with the outer conditions like humidity, light. So that's they matters a lot. Okay, the viscosity of the photoresist while spin coating, so how much thick you will get the resist thickness. Okay, that also adhesion, if there is no adhesion there is no point of coating the photoresist. Okay, so that will get removed during the development. Okay, so there won't be any, you won't get see any pattern over the photo or the wafer. And contrast curve, resist contrast curve, so that should be kind of very sharp. Okay, that should be kind of very sharp like this. Okay, if the resist contrast curve is like this, so this is not good, because if there is kind of some because of that you won't get the features properly. So in this one what will happen is the thickness, if you have somewhere there is more thickness, somewhere there is less thickness, so that will get removed in this one properly, but in this one that is a very that is a bit hard. Okay, that is a bit hard, so you need to give beyond this dose. So dose required is more, and this same thing will get replicated over the on the on the substrate. Okay, so kind of different kind of profile you will get. Okay, so and a resolution, a thermal stability. So these are kind of critical parameters for the resist that is required. And charging is kind of when you are doing the e-beam lithography, because in e-beam lithography we there is a electron gun. So electrons are writing the pattern over the because of the electrons there is change in the resist. The properties are changing due to the electron. Okay, electrons. So that should not get charged, otherwise that will you won't get the desired feature size, because they will repel the electrons. The electrons will the beam will diverge because of that. Okay, so in substrate compatibility, the substrate should be it should be compatible with the more and more number of substrates like glass, quartz, silicon, gallium nitride, sapphire kind of substrates it should be compatible with. And process compatibility, after the process what you are doing, if you are doing the subtractive process, that should this your resist should withstand with that etching process. Okay, otherwise if the resist is also etching, then there is no point. Now let's go to the move to the subtractive process. Okay, so now what you have done is you had this kind of wafer. Now you have transferred the pattern over the substrate. This is PR, this is silicon. Okay, now or silicon dioxide, this is silicon dioxide, whatever. So now you want to remove the silicon dioxide from this point. Okay, this point you want to remove. Now you can do the now you this is the subtractive process. You want to remove the particularly from this point, and for that you have protected this part. Okay, not this part and this part with the photoresist. Okay, now okay now when we do the etching, that is kind of that can be wet etching or dry etching. In wet etching we use the liquid chemicals. In dry etching this is removed with the gases. Okay, the ions or gases, they will react with this part and they will remove directly. So that is, and in this wet etching there are some chemicals, they will react with this, they will make the complexes, that complex will get dissolved and that will be removed. That is the thing. Okay, what are the figures of merit of the etching? Like what is the etch rate? Okay, etch rate, all these things we will discuss in detail in the subsequent slides. Etch rate and the etch rate uniformity and anisotropy and selectivity. So these things that we will see in the subsequent slides. Now let us come on the etch rate first. In etch rate is the let us say that you have the d naught thickness and then you immersed this in a liquid for time t, and after that you are getting a d1 thickness. Okay, d naught minus d1. Okay, that is the delta d. This much of your resist is removed. Okay, so the etch rate is delta d by t. Okay, how much thickness with respect to time is getting removed, that is the etch rate. Okay, change in thickness with per unit time, that is the etch rate. So that is required because you need to know this, how much this exposed area, that is the exposed area, how much you want to etch. Okay, how much material you want to remove, that for that time only you will keep that substrate in the solution. Okay, that is the thing. Now uniformity uniformity also plays a very critical role, because that is maybe under etched, over etched. That is the thing. So if huh, uniformity, okay, because of this feature sizes, okay, because of the feature size, that the feature size is high in this area, this is medium, this is very small feature size, and the etch rate also depends on the on feature size. Okay, that we will see in the subsequent slide, why this actually depends on the feature size, because okay, there is a fresh solution that should go inside, and that should remove this material. Okay, to reach this fresh solution here, there should be removal of the product as well. Okay, so they at the same point, and also that depends on the uh, on uh, on the viscosity. Okay, how much viscosity is there? More is the viscosity, that will be very problematic for the fresh solution to go inside and remove the material. Okay, so that is why there is a non-uniformity because of the feature size. And this the agent or material or chemical, or that solution, the agent solution which we are using, that should be such that it should not be very sensitive to the feature size. Okay, and also not to be very sensitive to the temperature and agitation in the sense, we just shake the petri dish wherever there is a solvent of, or this agent is there, so that it can go inside. We agitate so that the product should get removed, that come out, and fresh solution can reach the bottom. Okay, that is, for that we do the agitation and increase the temperature to increase the diffusion of the fresh solution to that. Okay, so now another one is isotropic and anisotropic etching. Okay, isotropic in all the direction, there is etching uniformly. Okay, so in this one, you can see this, as we increase the time, there is a under etch also, this under etch, that is because of the this developer or this etchant that we are using is uniformly etching in all the directions. Okay, and this anisotropic etching, that is, in anisotropic etching, what happens is, uh, yeah, particular surface is more etched as compared to the other surfaces. Okay, that is the anisotropic etching. Now, okay, there is okay, let us say we have had this is the photoresist, and we wanted to etch this layer. So we wanted to etch this part only because of the isotropic nature of the etching. So what will happen is, there will be a under etch as well. Okay, this is dm we wanted, but what we got is df. Okay, this df minus dm, this is the undercut, this much plus this much is the undercut. Okay, so so that is what we didn't want it. Okay, c is equal to undercut, and this is also when you wanted a pillar, but because of that you are getting this kind of profile because of the undercut. Okay, no, let me do it. Okay, okay, now the selectivity. selectivity, as I told you, we are depositing photoresist to protect this layer. Okay, at this point we have photoresist, at this point we have photoresist, so that for the further processing after the lithography process, we do two kind of things. One is the additive process, one is the subtractive process. Okay, so if this subtractive process, we are doing the subtractive process, so there is during that subtractive process, this material is the photoresist material is also getting etched. Okay, and this material is also getting etched. So okay, what is the rate of etching of this material and what is the rate of etching of this material? So the rate of etching of this material, whatever that masking layer, okay, that can be anything, masking layer we can say, just masking layer. Okay, this material should be lesser than the rate of the this one. Okay, so the selectivity SAB is given by rate of etching of the film, which is this one, to the ratio of this one to the rate of etching of the photoresist or the masking layer. Okay, now this is the like representation of the of wet etching. So how does it happen? So there are these marking done. So this is the etching mask which is protecting the layer underneath. Okay, so and there is the solution, which is this is the complete solution. Okay, this is the complete solution. Okay, so what will happen after this etching? During the etching, there is a stagnant layer in between these two. So that layer is doing nothing, but it is there, which is doing nothing. Okay, so through that stagnant layer, so that you must have seen during the CVD process as well. So there is when there is a flow of the gas, there is a stagnant layer which is near to the surface. Okay, so what happens, the diffusion happens, diffusion of the gas happens through that stagnant layer. Okay, so which is used for the deposition. Here it is used for the etching, for the removal of the material. So initially this first process and this third process, okay, this is diffusion. First and third is the diffusion of the material. One is the in diffusion, one is the out diffusion. This out diffusion is nothing but the product. Okay, whatever the dissolved product of the film, that is we are removing. And second process is the kinetics. So the reaction between the etchant and the film. Okay, class. Reaction between the etchant and the film. So the reactant, the fresh etchant should be transported through this stagnant layer. Okay, that is required. This selective and controlled chemical reaction. At this point, that this reaction should be very selective to this film, not with the etching mask. And transport of byproducts away from the products through this third one. Third one is the transport of the byproducts. Okay, from the this surface to the outside, so that fresh etchant can come. Okay, so now that we have seen during the CVD as well, there are what is the bottleneck. Okay, so if surface reaction rate limit, that can be surface reaction rate limited. The reaction is too slow, but this etchant is available, but the reaction is too slow. Okay, that can be the one case. And another case is the reaction, the diffusion of the reactant through this stagnant layer is very slow, but reaction is too fast. Okay, that is the another case. So So the surface reaction rate limited, the reaction is too slow. Okay, so that is the chemical reaction between the film and the etchant is very slow. The diffusion across the stagnant layer is very slow. That is the bottleneck. The diffusion is the bottleneck, then one is the reaction is the bottleneck. And this H rate at this point, if this is reaction rate limited, depends on the temperature. Okay, if we increase the temperature, that can increase the kinetics of this reaction in the step 2. Okay, that depends on the K, which is the reaction constant K. Okay, that can be we can make it faster if we increase the temperature. Okay, so that can be done. Sorry. Another one is the diffusion rate limited. The diffusion rate limited is because of the your HND is not okay. HND is not there. I mean to say HND is not sufficiently available at this point. Okay, the amount of HND is not available at that point. Okay, so what we can do is we can just agitate it, or we can just agitate it. We can just so by that the agent will the product whatever the products are there at this, they will get removed because of the agitation. Okay, so this stagnant layer will get removed because of the agitation, and because of that the fresh solution can come and that can react, or because of for that we can do the because of that we can increase this diffusion. Okay, if we can increase this diffusion. So conditions, so when there is surface rate limited at the low temperatures because of the dilute agent, because dilute agent is the molecules of the agent are very less. Okay, we diluted in the solvent, or the weak agents. Okay, that is the case. And if we at higher temperatures we can at high temperature, what will happen is the reaction is faster. Okay, reaction is faster, but diffusion is not that much faster. So because of that there is diffusion rate limited. If this agent is viscous, highly viscous, so to diffuse the fresh agent from the top to through the stagnant layer, that will be very difficult. Okay, and aggressive agents, so agents are very aggressive, so the reaction is very reaction rate is very high. So during that also this is reaction rate limited. No, this is diffusion rate limited. So how the surface finishing will be there? So in surface reaction rate limited, there is kind of rough surface, maybe anisotropic, and during the because of the diffusion rate limited, the surface will be shiny and smooth. Okay, these are the things that is there. Now the oxidative etching. So there are some things, the agent, which agent is used for which material removal. Okay, that we will see now. Okay, there is oxidative agent is it oxidizes the surface and then removes it. Okay, so that is the oxidative etching. So most of the agents involve oxidation of the surface and then they removes that surface, that material. Okay, like if the surface is silicon, that will first convert Si to SiO2, and then this will get removed by the HF kind of, either HF, or there are some other materials as well, other agents as well. Okay, which do not use HF. Okay, so okay, most of the deposition are oxidative or are reducive. Okay, so first there in CVD that we have seen the reduction there is reaction. the material gets reduced over the substrate. That's how that gets deposited. Now for the removal of the material, we are oxidizing it at first and then we are removing it. Okay. So oxide needs to be dissolved in some acid or base medium that we will use. Okay, so we will see these things. Okay. Now HF. Okay, HF is used for the SiO2 etching that I told you. So commercially available HF is 49%. HF is there in DI water. So then that further it is diluted for the purpose. Okay, so during the HF etches silicon. How does it etches? SiO2 is reaction happens with HF and it is converted into H2SiF6. Okay, this H2SiF6 is dissolved in water. Okay, that's how it is getting removed. So during that process, during the SiO2 etching, the HF is consumed, H ions. Okay, these H ions are the change in concentration. Okay, so during that process, initially were HF was there, so the concentration gets decreased as the etching process proceeds. Okay, so the etch rate will also not be constant because of that, because it is getting reduced. So what you can do is you can make a buffered solution that will make a concentration of HF constant during that process. So in this one, what it will give you, NH4F plus NH3. NH4F will give you NH3 plus HF. Okay, so this will make the reaction rate constant, and we can call it buffered oxide etch. Okay, buffered oxide or BOE. Okay, buffered oxide etch. And you can this may contain some surfactants as well to improve the wettability of the silicon. Wettability in the sense, if the silicon, when you pure silicon is if there is no oxide layer over the silicon, when you just put a drop of water, that is kind of hydrophobic. Okay, that you can see, and that if there are surfactants that are there in the solution, in the etchant, so that will improve the wettability and improve the reaction rate. Okay, that is what now this is the curve for the etch rates. Okay, for the etch rates, what is the etch rate for what dilution of HF? So HF is 1:1 in DI water. So the etch rate is very high. Okay, that is above 1000 angstrom, okay, per minute. That is above 100 nanometer. Okay, kind of 100 nanometer per second per minute. Okay, that is the thing. So if you decrease the concentration of HF, okay, decrease the concentration of HF, the etch rate will also get reduced. Okay, this is the etch rate, and this is the concentration. If you increase, that is the simple case. Okay. More the availability of HF for SiO2 reaction, that more will be the reaction. Okay. Now sometimes silicon nitride, you want to etch the silicon nitride. So in this one we haven't the protecting layer. Okay, protective layer we will talk about, I think in the subsequent slides. I have included that protective layer. So silicon nitride etching. So these BHF or HF can be used for the silicon nitride etching. I think someone is there in this meeting. No one. Okay. In silicon nitride etching, So BHF HF can be used, but etching is much slower than SiO2. Okay, so this is kind of typically 0.5 nanometer per minute for the very high quality layer of silicon nitride. Okay, so this is very less, so it will take hours to etch this 50 nanometer of silicon nitride. Okay, that will take 100 minutes. No, the time is too high, so also this you do not want. And photoresist is not a good masking layer, because photoresist will also get dissolved in the HF. Okay, that HF will etch the photoresist, so it will be not good. So because if you have this silicon and over this you have silicon nitride Si3N4, and over this you have photoresist, and you want to etch this material. One second. Okay, now you want to etch this material silicon nitride from this part. Okay, from this part. So as the etch rate is very less, like 0.5 nanometer per minute, and for like 50 nanometer you want to remove, so 100 minutes it will take. And during that time, this photoresist is also there in that solution. Okay, so in 100 minutes this photoresist will also get removed, and the upper layer of this part will also get removed. Okay, you will find a very a less thickness of silicon nitride over here than it was expected. Okay, so that is the thing. So what you can do is H3PO4 is used for when silicon nitride and SiO2 stack needs to be etched. So in this case, silicon nitride etch rate is 10 nanometer per minute, and SiO2 is 1 to 2 nanometer. So in this case, the selectivity that we were talking about is 5 times higher. Let us say the 2 nanometer per minute it is removing the SiO2, then you can use SiO2 as a masking layer. Okay, so in this case what you can do is, this is this is silicon nitride Si3N4. Okay, and also you have here you have patterned SiO2. Okay, SiO2, and you want to protect this part of this SiO2. Okay, then silicon nitride. Now you can etch, you just need to have sufficient SiO2 over that. Okay, for this you need, for 100 nanometer of silicon nitride, you need around 20 nanometer of SiO2 that you can do deposit with PCVD or anything that within several minutes. Okay, 20 nano. For the safer side, you can do 30 to 40 nanometer of SiO2. Okay, and that will be good. And then just put in the HF, because in HF SiO2 rate is very much faster, so you can just remove the SiO2. Now this etch, now this etch rate is also dependent on the process through which you have deposited the layer. Okay, the quality of the film, deposition method, temperature, and impurity in the layers. So the etch rate depends on these factors. The high quality film, that is the high density of the film, the etch rate will be lesser. The deposition method that you use, deposition method is like if you are doing PECVD or CVD method for the SiO2 deposition, and with another wet oxidation or dry oxidation you are using for the SiO2 growth. So certainly you will get a very good quality of the film in the oxidation, in dry oxidation. Okay, due to the dry oxidation process, through the dry oxidation process, the H rate is lesser in that case. Okay, so this is thermal oxide, and this is PECVD. Okay, so this is 90 to 100 nanometer per minute, this is 300 nanometer per minute. Can you see the difference? The difference is pretty huge. Okay, so now how many slides are left? Okay, now the isotropic silicon etching. Okay, now what you can do is, an isotropic is like it is etching everywhere. Okay, so you can use hydrofluoric acid, nitric acid, and acetic acid for the silicon etching. So what hydrofluoric acid, HF doesn't etch silicon. Okay, but HF can etch SiO2. Okay, first this nitric acid will convert silicon to SiO2. Okay, not the nitric acid, but HNO2 will convert that thing. Okay, so the simple thing is HNO3 will oxidize to SiO2. This developer will dissolve, this HF will dissolve SiO2. Okay, it will etch SiO2. Okay, then for the transportation purpose, or the solvent is used CH3COOH instead of the water. You can use water as well, but there are other effects that will come. That's why we are using this acetic acid, that we will see why we are not using this H2. Okay, so redox reactions are happening at, because in previous session I also told you about the domains. Okay, the domains are created, positive and negative domains are created over the substrate. Okay, and these domains are not static, they are just random domains, and they are changing their polarity, not the polarity, they are just kind of moving on the substrate. Okay, so because of that there is a redox reaction happens, electrochemical reaction happens, oxidation at anode and reduction at cathode, and this is a redox reaction. Okay, and points on the surface randomly become oxidation and reducing sites, and over time the difference is averaged out, because that is, these kind of domains are just random and they are kind of moving. So this is like the average current is 0 in an when there is a semiconductor, but electrons are moving in the random directions, but that average is out to a 0, because electrons at the same time, one electron is moving at this direction and the other is moving in this direction. Okay, over time that difference comes to, average is out to 0. So that is the thing. So so there is an oxidation, Si2 converts to Si2 plus, and reduction at cathode, so NO2. So from where this NO2 will come, that we will see from the HNO3. From HNO3 this will give you NO2. Okay, so that HNO3 will react with will give us the NO2. Okay, this NO2 will give will take 2 electrons and will convert it into NO2 minus. Okay, so now this will form the silicon hydroxide, silicon hydroxide, and that will be converted into SiO2 plus water. This is dissolved. So now SiO2 is etched in HF. Okay, which will form H2SiF6, and that is soluble in water, and that will be removed. Okay, first we are converting silicon to silicon dioxide, and then silicon dioxide is dissolved in HF, and that HF is silicon dioxide, the SiHF6 and H2SiF6 is getting removed. So now let us see, so how we are getting NO2. Okay, how we are getting NO2, let us see that point. This is HNO3. Okay, HNO3 is like this is acid, so it will give H ions, so NO3 minus plus H ions. So because of the impurity of HNO3 itself, there is some amount of HNO2 inside that. Okay, that HNO2 will react with HNO3 and will give you NO2. Okay, this NO2 will give you and will take 2 electrons that which were released by there is an because of anode and cathode reactions, because of the random domains, that reaction will happen. Okay, this reaction will happen, and because of that you can you now then this 2 NO2 minus will give you HNO2 again. Now you are getting NO2 as well and HNO2 as well, because of one molecule. We started with one molecule of HNO2 and finally we are getting 2 molecules of HNO2. Okay, so over time you will get more and more HNO2, reaction will get faster and faster. Okay, so HNO2 is required. Thankfully some of the spontaneously generates in HNO3. So because of the impurity, this is generated in HNO3 itself, and that will be used. Okay, now what is the role of, okay, now we will see what is the role of the acetic acid. Okay, in instead of water. Okay, so because of the high dielectric constant of H2O, that will actually shield the charges. Okay, so the CH3COH, that is the acetic acid, has very low dielectric constant, and that will allow the reactions to happen. Okay, and less dissociation of HNO3. Because of that there will be a less dissociation. Okay, and this HNO3 will be there, more oxidation, and there is some kind of that you can read on the internet. I just a bit of part that I forgot actually, so that you can see. Okay, next we can see, and hydroxides. Now the hydroxide silicon etching, previously we used HF to etch the silicon. Okay, now directly without using the this combination of HF plus nitric acid plus acetic acid. Okay, HNA, that was the HNA. First it was converting silicon to silicon dioxide, and then we were removing the silicon dioxide. Now this hydroxide, NaOH, KOH, TMAH, these can directly remove the silicon. Okay, they will form a complex, this SiOH whole twice 2 plus. Okay, and this will react the formation of the soluble complex. This will react with OH minus, and this complex is soluble in water. Okay, so one oxidation is happening and at anode, and this reduction is happening at cathode. So this will give you a soluble complex. Okay, without the usage of the of any kind of HF. Okay, so you can use this. So but this agent, this NaOH and KOH, this agent contains metal ions, so you cannot use these agents for the processes for the if After this, you are doing the CMOS kind of processes, you cannot use this thing. Okay. With KOH also you can do, because of the metal ion contamination you cannot use to it uh, for CMOS processing. So use the dedicated tweezers, beakers and hoods, because no metallic tweezers you cannot use. Okay. And beakers, like soda lime glass or these you cannot use because there is sodium in them, so you need to use quartz beakers for that. And uh, for the highly doped silicon, this KOH reaction stops. Okay. And this anisotropy is very high for 110 surface. 110 surface H is much faster than the other surfaces. So 111 is the least kind of, it doesn't get etched. Okay. 111 surface. So you can use silicon nitride as the masking layer. Okay. So, and SiO2 also, SiO2 and silicon nitride as a masking layer for silicon. So that is, silicon nitride is much better than that of the silicon dioxide, but silicon dioxide is very easy to deposit. Also silicon nitride for if you are doing PECVD kind of. Okay. So for the CMOS processing, you can use this trimethyl tetramethyl ammonium hydroxide, not trimethyl, tetramethyl ammonium hydroxide. So there won't be any contamination, metal contamination kind of thing. Okay. This also stops at the highly doped region, and anisotropy is low in this case. So anisotropic, so and selectivity is again very good in this case. Okay. So this is the thing. So because of this plane oxidizes much faster, which in hydroxides. Okay. Hydroxide KOH or something, because for if this plane gets oxidized is very much faster, 111 plane gets so that oxide layer SiO2 will that SiO2 layer will protect the underneath layer of the silicon. So that is why this surface gets less kind of etched. 111 surface, the etch rate is very less. Okay. So that is fine. So, and we are not using the HF, so that is why anisotropy is there. If we would have used the HF, so whatever oxidation is there, that would get removed. Okay. So because in oxidative process in HNA, that is the where we use HF, nitric acid and acetic acid. So in that case we deliberately oxidize the surface. In this one it is getting oxidized, and that oxidation is inhibiting the etching of the underneath silicon layer. Okay. And so for today we can stop here, and if you have any doubts you can ask me, and you can write to me. Okay. Yeah. Thank you for your time.